Okay, so welcome back to chapter 11. Now we're going to start discussing the outer solar system. And so we're going to start with some of the most beautiful and interesting parts of our solar system, which are the giant planets. So you'll notice here, we're just going to say giant as much as possible to follow the book. You may have heard these called gas giants, and we're going to see why there's a little bit of tension with that label and how we might better classify them. Okay, so what are the outer planets? Well, after Mars and the asteroid belt, which we will talk about the asteroid belt in a coming chapter. So beyond that is the realm of these giant planets. And this is, like I said, a really important area of the solar system. So by mass alone, if you add up the mass of all of the planets other than Jupiter, it would still be less than the mass of Jupiter, which is kind of crazy. So a lot of these pictures, like this one, for example, are not quite to scale. Saturn is pretty significantly smaller than Jupiter. Now, each of these outer planets has plenty of moons, and many of those moons are basically worlds of their own that have plenty of interesting things going on, and we have a whole chapter dedicated to them and what we've learned about them. Now, when we talk about the structure of these outer planets, you'll typically hear them called gas giants by non-astronomers. In astronomy, we tend to call Jupiter and Saturn gas giants and Uranus and Neptune ice giants. Now, when we use these words, we have to be very careful. Now, remember that these are huge planets, so they're huge clouds of stuff. And when you have a bunch of stuff in space, what happens is its own weight is going to squish it down and compress it, right? Like imagine that you're laying on the ground and an elephant comes and steps on you. That's a lot of material above you, and you would definitely feel it. So now consider a planet where we have, if you're partway into Jupiter, you have a huge amount of stuff above you. It might be like gaseous stuff, but it still has a weight to it, and it still would be exerting a pressure similar to our atmospheric pressure, but just much, much larger. And so what this means is that the materials, we're going to call them gases, ices, and rocks, but they're all going to behave really, really differently. And in particular, the gases in these giant planets are often actually in liquid form. So you might know that if you cool down air enough, that it becomes like liquid nitrogen and liquid oxygen. I encourage you to look these up if you haven't seen them before. We can use them to make ice cream and so on. Now, it turns out even if you're somewhere relatively warm, which these planets are quite cold already, but even if you're somewhere relatively warm, if you have enough pressure, that can also cause gases to become liquids. And so when we say gas giants or gas planets, these are actually closer to liquids or even like solids almost, but they are made out of hydrogen and helium. Now, the ices, which are the primary sort of composition of Uranus and Neptune, these are just our name for more sort of volatile compounds. So things like water, ammonia, hydrocarbons, methane, all these sorts of things. We're going to call them ices. Now, they sometimes are solid crystal ices, but again, sometimes they're going to be liquid, sometimes they're going to be in weird states of matter that we can't easily imagine as humans. And then finally, rocks. So there are rocks, mostly the moons and the rings, and sort of the core, the center of these planets do have some solid stuff in them. But again, these rocks, this is just our name for anything that's not a gas and an ice, and it can be in a variety of states of matter, not just like the rocks we have on Earth. It can look quite different. And what I want to highlight here is that there's a surprising amount of water in these outer planets. And actually, the reason for this is that most of the stuff in the universe is hydrogen, and there's actually not that much oxygen. And so when we have a lot of hydrogen and a little bit of oxygen, we tend to get water forming. And so we're left in, again, this type of reduction-dominated environment, like we talked about a few chapters ago. So what does it mean to be a reduction-dominated environment? Well, it means that there's not much free oxygen to react with things. And so instead of oxidized materials like we see on Earth, right, iron rusts, that's oxidation, In the outer solar system, we don't tend to see that very much. We see things being reduced. So the chemistry can be quite different, and things that are unstable on Earth are actually quite stable on these outer planets. So, okay, how do we know about them? Well, from Earth, we see the outer planets as just little dots in the sky. With a telescope, we can start to see some details on them because they're so large. But to really understand them at all, we have to actually send stuff out to them. As you can imagine, this is quite difficult. So there have only been a handful of missions, like under 10 missions to the outer solar system. I list a few challenges here. So while it takes a few months to get to Mars, it takes years and then even decades to get to the outer solar system. So these are really long-term missions. There's a significant communication lag due to the speed of light. So remember, we talked about how from Earth to the sun is an 8-minute delay. When we're going from the Earth to Jupiter, this is a much, much longer delay, and we'll talk about how long, but we're starting to get to like almost an hour of lag each way. So an hour there, an hour back. So if something goes wrong, it takes an hour for you to hear about it, and then it takes another hour for you to tell your spacecraft how to fix it. We also have to go through the asteroid belt, which, as you'll learn in your homework, is not actually that dangerous, but there's a lot of dust there, which can cause a problem. We have to navigate the strong magnetic fields, especially from Jupiter. We cannot use solar power typically, so we have to use nuclear-powered spacecraft. There's just not enough sunlight when we get to the outer solar system, and that just adds another layer of design difficulty. We have to fit a little nuclear reactor inside our spacecraft. We also have to do some very precise physics to calculate where the planets are going to be so that in 10 years, when the probe finally gets there, it's in the right spot. So that alone is a pretty significant challenge. So the first mission that humans sent out this far was Pioneer 10. That was sent in 1972. And it was able to visit Jupiter, and we sent its twin, I believe Pioneer 11, to go visit Saturn. And then the really famous ones are Voyager, so Voyager 1 and 2, and these went on a very special route. It's so lucky that they were launched in the 70s when they were, because once every 175 years, there's a path from Earth to the outer solar system that happens to pass by every one of these planets. And so they were sent on this path. Voyager 1 was sort of slingshot away from Saturn, so it could go explore sort of the empty space of the outer solar system, whereas Voyager 2 continued on to Uranus and Neptune and then has kept going, and it is still going, and we're still able to talk to it. And actually, one of my professors when I was an undergrad worked on the Voyager 2 mission, and it was basically all he's done, right? Because it was launched in the 70s. He's an old man now, and it's still going, it's still sending data, and he's still processing it and telling it what to do. Now, it's been slowly dying. As it gets older, parts of it break. They've had to sort of redirect power as they start to lose the power supply, but they've managed to keep it going. It's really incredible, and these are the first human objects to get to the edge of the solar system. So really wonderful feat of engineering, and I encourage you to look into more about how difficult it is to communicate with them, to design them, and so on. But this is just to highlight sort of these challenges. Now, these probes, Pioneer and Voyager, were sent sort of as flyby missions. So they went to a region and then they kept going. But we also have orbital missions that we've sent out. So these are Galileo, Cassini, and Juno. And so all three of these missions actually, instead of doing a flyby, we sent them to become satellites of these outer planets, which just gives you a lot more time to collect data rather than just as you zoom past. The downside is that you can only go and study one place, right? You have to pick which planet you want them to orbit. So Galileo and Juno both are orbiters of Jupiter, and Cassini is an orbiter of Saturn. So far, there have been no orbiters of Uranus and Neptune, although people have planned it. It just takes a long, long time, right? to get something out there and to start collecting data. So what did these orbiters discover? Well, Galileo was mostly present to study the atmosphere of Jupiter and its moons. And like I said, we'll have a whole chapter on these Galilean moons. They're very, very interesting, even more so than most of the planets. And Galileo also sent an entry probe down into the atmosphere of Jupiter. So it was launched with a parachute down into Jupiter, and it collected as much data as it could before it sort of burnt up in the atmosphere as it, like a meteor coming into Earth. And we'll talk about some of its findings in a few slides. Juno was around Jupiter, and you see it's much larger in this diagram. It was sent around Jupiter to measure and experiment with its magnetic fields. So we'll again talk about Jupiter's very interesting and surprisingly strong magnetic fields. And so that was the primary mission of Juno. I believe it was Juno where they originally didn't want to put a camera on it, and basically public pressure convinced them to add a camera so that we could get some additional beautiful photos from up close. And then lastly, Cassini was the sole orbiter of Saturn, and it was sent similarly to study the structure both of the atmosphere and the rings, and to study the moons of Saturn, particularly Titan, which is very interesting. And it had its own entry probe, which actually went and landed on the moon Titan. And again, in a future chapter, we will learn a lot about Titan and see how magical it is as its own world. I just want to highlight this picture in the bottom right from Cassini as it orbited Saturn. You can see the rings there. And that little dot with the arrow is actually Earth as visible from Saturn, which is pretty crazy that we can take such a photograph. Okay, so let's take a brief overview of the outer planets. So these are pretty far away. If you remember from your last homework, the outer solar system starts to be stretched out more and more. These planets are pretty separated. And so Jupiter is already 5 times farther away from the sun than Earth is. And Saturn is about the same distance from Jupiter as Jupiter is from the sun. So you can see how they start to really space out. By the time you get to the distance between Saturn and Uranus, that's the same as the distance from Saturn to the sun. So you see how this just gets progressively more and more sparse, basically. And that's because these giant planets, when they formed, they sucked in all the gas and ice from a pretty large region around them. So they cleared their orbits out, and it all sort of went into forming their structure. So Jupiter and Saturn, you'll often hear these called gas giants. They have a really similar structure. They're both made mostly of hydrogen and helium. Jupiter is 5 times more massive than Saturn, and it has a slightly bigger density. So you'll notice that Jupiter has a density around 1.3, Saturn 0.7. So like I mentioned before, Saturn is actually such a low density that it would float in water if you could put it in water. And this just comes down to the fact that because it's smaller, its gravity is crushing it a little bit less, and so we don't get quite as high of a density. I want to highlight that these densities are typical of liquids on Earth, whereas these planets, right, we call them gas giants. So you can start to understand how the gas inside of them has to be squished so much that it effectively becomes a liquid. Uranus and Neptune are a little bit different. We often call them ice giants because they're made more of these volatile materials like water and methane and so on, that whether they're solids or not, we in astronomy, especially planetary astronomy, call them ices. So because of this, they have a little bit higher densities despite their small size, right? So we saw how with Saturn, it's a little smaller than Jupiter, so it has a lower density. Yet Uranus has the same density as Jupiter despite being much, much smaller. That's because it's made out of different stuff. And of course, as we get to the outer solar system, maybe something that's obvious, but it's worth mentioning, is that the farther we are from the sun, the less solar energy is available. And we're going to see this makes the outer planets really special places. So they still have plenty of energy, but they get it from a multitude of sources. We'll see what we mean by that. So what is the appearance of these outer planets? Well, when we look at them, what we're seeing is the upper atmosphere. And that might sound weird, right? Because these planets, while they have rocky cores, they're not like Earth, where the majority of it is a bunch of silicates and metals and stuff. So Earth, right, has the ground and it has the sky. Whereas for the giant planets, that's not such a clear distinction. So they still have an atmosphere, but beneath that is just more, gases and ices. They may be liquids, of course, but so it's a little more complicated. But just to highlight what we see, which is the upper atmosphere. So on Jupiter and Saturn, we're mostly seeing ammonia clouds. And when it's just pure ammonia, those are the sort of paler white regions. And when it's sort of chemicals that are reacted with the ammonia, this is also something that happens in the deeper layers, we see these darker regions. So those are the clouds, right? The cloud cover. But of course, beneath the clouds is not dirt, but more complicated stuff that we will discuss. So on Neptune, Neptune and Uranus, we're seeing methane clouds. Now on Neptune, that darker color of Neptune, which we'll see some pictures of soon, is due to sort of pure methane clouds. Whereas on Uranus, the sunlight breaks the methane apart a little bit into a haze, so like a smog almost, which makes it this lighter pale color. And so just to reemphasize this, what we see of the planet is just the most outer layer of its atmosphere. And so that's not necessarily representative of what the structure of the planet, what it's made of. Okay, so what about the rotation of these planets? Well, if I had to summarize it in one word, it is fast. So these planets rotate pretty darn fast, especially given how big they are. So when we look at them with telescopes, what we're seeing is not the rotation of the planet, but we're seeing the motion of the wind, the clouds, right? So just like on Earth, the clouds kind of move as the planet rotates, but they're not necessarily the same speed. So in order to measure the rotation or the day, how long the day is on these outer planets, we really need to use radio waves. So radio astronomy, both bouncing them off the planets, radar astronomy, and just observing them. And so doing that, we find that the outer planets have days ranging from 9 to 17 hours, so all shorter than an Earth day, and they're all much, much bigger. So what this means is that the material is moving really, really quickly. Now, in addition to the rotation, we can also talk about the tilt of the planets. So Jupiter is weirdly not tilted. It's almost sort of vertical relative to how it orbits. So if we imagine the ecliptic plane, right, that's what we measure tilt from. The Earth is tilted, that's why we have seasons, about 23 degrees, whereas Jupiter is almost sort of straight up and down. And this is related to the fact that Jupiter is really big, so it was harder to disturb it due to collisions in the early solar system. And collisions are our primary hypothesis for how planets become tilted. Saturn and Neptune both have a moderate tilt, so similar to Earth in the sort of high 20s of degrees. And as a result, they both have similar to Earth seasons. Obviously more complex when the planet has not much solid ground, but they do have some sort of seasonal variation that we can see in the atmosphere. Uranus is the really weird one. So Uranus is the only planet that has been knocked sideways. So it has a sideways rotation, 98 degrees. That means if you imagine the equatorial plane, Uranus is rotating with its axis in the plane. Okay, so Jupiter is straight up, whereas Uranus is almost completely on its side. And so what that means is that Uranus has super dramatic seasons. So we have a picture of it here, and we've also labeled some of its moons and rings and so on. And so if you imagine you're on one of the poles, let's say the south pole of Uranus, then as it orbits the sun, because it's rotating on its side, you will have an incredibly long day-night cycle. So you will have a 42-year day and a 42-year night. Whereas if you imagine being on the equator of the planet, you would have kind of an equally weird time as you have the day-night rotation, you would just see the sun kind of stay at roughly the same height in the sky for 42 years. So kind of crazy. Okay, so finally, let's dive into this composition and structure, what we understand of it. So, like I mentioned, we have to keep in our brains. We're so used to hearing gas giant, and we often, even in astronomy, call Jupiter and Saturn gas giants. But the material that forms them is only partially gas. Okay, Jupiter and Saturn are majority hydrogen and helium, but especially for Jupiter, as we go down farther, so this gray region in Jupiter, a large portion of it is liquefied hydrogen. So it's been turned into a liquid as we've squished it more and more. And you can look up pictures online. We can make liquid hydrogen on Earth. It just has to be very cold. Now, beneath that, it's even weirder. We get what's called metallic hydrogen, and that's where the hydrogen liquid is squished so much that the electrons are able to start to move around, and it becomes conductive, like a metal almost, but it's still just made of hydrogen. And that conductivity is actually what leads to the magnetic fields of these planets. Remember, to have conductivity or to have magnetic fields, you need a liquid, like on Earth, a liquid iron, something that is conductive. Okay, and then if you go even deeper, you see that there is some small region, the core, which is rock and ice, and that's just sort of whatever has fallen into the planet or whatever was the nucleus that started its growth, and the gas all was sort of pulled into. That's what we find in the center, but you see it is a pretty minimal portion. So this is why we consider these giant planets to be different from the terrestrial planets. It's not just that they have a really thick atmosphere, it's really just that the majority of the planet is gas or ice. Okay. We see something pretty similar for Uranus and Neptune. So the outer portions of the planet are mostly hydrogen and helium. But the majority of the mass of the planet, right, 60% of the mass, is in the form of these ices, water, ammonia, methane, all these sorts of things. Now remember, what we actually see of the planets is mostly what's in the top layers of the atmosphere. That's different from the composition that we list here, right? So on Jupiter, most of what you see is ammonia clouds, even though the majority of the mass of the planet is in hydrogen and helium. Okay. And so, yeah, additionally for the ice giants, Uranus and Neptune, we see that the cores are larger relative to the size of the planet. So they have about the same size of core as Jupiter and Saturn, but there was just less stuff near them in the formation of the solar system, so they didn't grow quite so much. And so as a result, a larger fraction of the mass of the ice giants is from the core. And so we want to hold all this in our minds, and we always want to remember that the way these materials operate, even though we call them gas and ice and rock, is very, very different from how they appear on Earth. Okay, so we talked about how these planets are far from the sun, and as a result, they get fairly limited sunlight energy, which if you think about Earth, that's where the most of our energy comes from, is from the sunlight. Of course, we do have some residual and radioactive heat inside the Earth that keeps it molten there. For the outer planets, this internal heat is really significant. So especially on, so Saturn is the planet with the most internal heat generation, given its like per size. But we see it on Jupiter and Neptune as well. Now, Uranus is really intriguing. Uranus has almost no internal heat generation. So as a result, we can conclude that Uranus is pretty well differentiated already, because the source of this heat, so part of it is, the planets just have some heat left over from when they formed, but the continual internal heat generation, that comes from material, heavier, more dense material falling inward. Okay, so it's crazy that this is still happening, right? These planets are billions of years old, but it takes a long time for such a big cloud of gas to collapse. And as things fall, right, if you imagine when you slap your hands together, you can feel them start to get warm if you keep doing it. the same thing is happening as molecules fall deeper and deeper into these planets. They collide and they produce heat. Now, this happens especially in Saturn because Saturn is less differentiated, smaller, so it has a different gravity, different gravitational field than Jupiter. And because of that, basically within Saturn's upper portions, little droplets of helium form, and these helium droplets sink in the hydrogen. The hydrogen is lighter, the helium is heavier, even though we usually think of helium like a balloon floating. Compared to hydrogen, it's heavier. So these fall, and because they're droplets, they have quite a bit of energy, quite a bit of oomph, and they are able to produce more heat. And so what do these internal heat sources do for the planets? Well, they produce convection currents. So they cause the planet's material to start to circulate, similar to how the internal heat of the Earth leads to the convection currents that create plate tectonics. And so this energy is really important to calculate and to understand if we want to see how these planets are going to behave and understand how they continue to operate the way that we observe them. Okay, and yeah, just to highlight the scale of this, so for Jupiter, the internal energy it produces from stuff falling still to this day is about the same amount as the energy from the sun that reaches it. So these are really significant features of the energy landscape of these planets. You can understand why we can't just ignore them when we try to analyze the physics here. Okay, so what about magnetic fields? Well, because we have internal energy, heat, and we have therefore circulation, and deep in these planets we have material like metallic hydrogen that's conductive, we find that the outer planets tend to have magnetic fields. So Uranus doesn't have much of one because it's not producing much internal energy. But when we look at Jupiter in particular, it has an incredibly strong magnetic field. And if you remember from earlier, Juno was actually sent out to probe that magnetic field, but scientists were able to detect that it existed long before that using the radio wave signals that we can observe, right, with those big satellite dishes on Earth. We observe them coming from Jupiter. And in particular, this is a throwback to our previous chapters, we see that there is more energy at longer wavelengths when we look at the spectrum of the radio waves from Jupiter. And that's really weird. That's not something we see with a black body spectrum. Remember, a black body spectrum has a peak, and that peak corresponds to a characteristic temperature. And as we go to higher and higher wavelengths, that shape falls off. There's less and less of those higher wavelength waves. For Jupiter, it looks pretty different. And so scientists realized that this was what we call synchrotron radiation. It's named after a type of particle accelerator, which is where humans first created it. And basically, it's what happens when you have a charged particle that moves around in a magnetic field. And so therefore, what we realized was, okay, Jupiter has to have a magnetic field, and there have to be some charged particles. Now, where are those coming from? Well, it turns out one of Jupiter's moons is full of volcanoes. You may have heard of it. It's called Io. And so it actually is spitting out lots of dust and gas with plenty of charged particles that then go on to move around in these magnetic fields, similar to the Van Allen belts on Earth that create the auroras. And so we see the radio waves that result. And so this bottom right picture here is actually a picture of those radio waves, obviously turned into colors so we can understand them. But by measuring the radio waves of Jupiter, we can get a really sort of interesting, helpful picture of the internal dynamics of the planet, right? When we see these radio waves, they're produced due to the magnetic fields, which are generated due to the internal motion and structure of the planet. So this is a window inside. Otherwise, it's very hard to see inside of these giant planets. Remember, we can only see inside of Earth because of earthquakes. And so we need something, some trick, right, in order to understand what's happening inside of them and to get that composition structure that we saw a few moments ago. Okay, so then zooming back out, let's talk again about the atmosphere. So this is the outer edge of these giant planets. And so for the atmosphere, we can actually look at the light that passes through it in order to see the spectral effects, right? Remember from our earlier chapters that when light passes through a material, some of those colors of light, the wavelengths, can be absorbed. And by measuring those missing spots, we can see what materials that gas or substance was made of. And so this chart here shows that. So the x-axis is the color, the wavelength. And the y-axis is the amount of light blocked. So the more light blocked, the higher the points are on this graph. And so whatever colors are blocked, those correspond to different materials. And we see some of those labeled here. So we have some water. These are all different parts of the spectrum that correspond to water being present. Now, when we look at some of these other points, some of them are going to be caused by other chemicals, maybe by ammonia, maybe by methane, so on and so forth. So this is how we are able to measure what these are made of. Now, if you remember, we also sent a little probe from Galileo. So as Galileo orbited Jupiter, it sent off a little spacecraft down into, to its death into the atmosphere of Jupiter. And that was able to make some more precise measurements. Now, unfortunately, the little entry probe, Galileo probe, entered in a very dry spot of Jupiter. We'll talk about that a bit more later. And so it wasn't able to collect much water, but it was able to see some of the other structure in the atmosphere, especially the ammonia content. Okay, so what about the clouds and the structures that we see? Well, the cloud formation that we observe, remember, this is the upper edge of the atmosphere of these planets. It's produced by some relatively complex dynamical processes. So looking at Jupiter first, we see on Jupiter that it has white and dark bands. And so the white regions are tiny ice crystals of ammonia. They freeze in the upper atmosphere, and they're able to form clouds, just like clouds on Earth. They're a similar color because they scatter light for a similar reason. And so that happens on the top of the troposphere of Jupiter. So the troposphere, it's hard to define, right? This is a word that comes from the study of Earth's atmosphere. But for these giant planets, it basically corresponds to the region of convection in the atmosphere. And so the upper layer of that's where we see these ammonia clouds. And when the convection currents cycle back down, these clouds get dispersed. We see the deeper regions of the atmosphere, these darker regions, which have a slightly different chemical composition, so some reactants from ammonia. So when we look at Saturn, because it's a smaller planet, the gravity is a bit weaker, so the layers of its atmosphere are thicker. And what we see on Saturn is that due to its high rotation speed, it has quite fast winds, which tend to disperse the cloud structures a little bit more. It creates this more uniform appearance. It's also a bit hazier. But something really interesting about Saturn is that if you look on the pole of Saturn, you'll see a really weird hexagonal shape. That's this rightmost picture here. As far as I'm aware, astronomers still don't have a great explanation of this. It's due to some very complicated dynamical physical processes with how the wind is moving around Saturn due to its rotation. But it's just one of the examples of the types of weird structures we get when we try to make a planet mostly out of gases or ices. Okay, so what about the atmospheres of Uranus and Neptune? Well, Uranus, that's the bottom left picture here, it's pretty darn featureless, not only in the visible, but also in the infrared and UV. And this is a result of the lack of an internal heat source. So remember, Uranus is already pretty differentiated. There's not much stuff falling anymore inside of it. And so there's not much of a reason for material to circulate up and down within the planet. It's still rotating because the planet's spinning, but other than that, there's not much happening. And so whenever the sunlight hits the methane in the atmosphere of Uranus, it produces a kind of smog, this haze, and that's what this pale color is the result of. Neptune is a little bit more interesting. So the darker color of Neptune is more pure methane clouds. And beneath that, we have seen that there are some hydrogen sulfide clouds as well. Now, Neptune also gets these little white splotches. These can also be formed from methane, but just at a different altitude, a higher altitude, where they reflect the light a little bit differently. So remember, Neptune, it has a similar composition to Uranus, but because it's still differentiating, it has an internal heat source, and that's why it looks so different. And so we can see this in this chart here, where we compare the atmospheres of the giant planets, and we see, so NH3 is ammonia, so we see for Jupiter and Saturn that it has significant ammonia clouds on that upper layer. Now, of course, there's also this orange upper portion, which is the haze that sort of disrupts and makes it look a little fuzzy. But the white or the paler portions of Jupiter and Saturn are from these ammonia clouds. And if those are being swept downward, then what we see are these deeper layers, which are other chemical compounds. Whereas for Uranus and Neptune, CH4, that's methane. So we see for Uranus that there's this significant haze above it, right? That's this reddish region, the hydrocarbon ices. Whereas for Neptune, the temperature is a bit more stabilized, and that internal heating causes much higher temperature deep within the planet. You see how the line within Uranus just kind of cuts off a little below 200 Kelvin. And so taking all this together, you can see how the dynamics of these planets are quite tricky. And even when they're made of similar stuff, if they have slightly different internal worlds, then we will observe quite different things when we look at them. Okay, so what about the winds and the weather on these planets? It's kind of weird to think about weather on these planets. There's not really a surface for things for like rain to fall on or clouds to be above, but there are still clouds, right? And so we can still think about what it means to have weather in these places. So one aspect of this is that basically, on Earth, we have phenomena like the jet stream that you may have heard of, which is where the air is being dragged by the ground as the Earth rotates, and that creates some pretty strong winds and currents. Now, the giant planets have this to an extreme. There's not like a continent in the way. There's not much solid material to have friction against. And so the winds on these giant planets can be incredibly strong. And so you'll see here in this chart that we're measuring eastward wind speed at a scale of hundreds of meters per second. So really, really fast stuff. On Neptune in particular, the wind speeds can become supersonic. So you can actually get, this is the bottom picture here of the equator of Neptune. You can get these clouds that basically are having like sonic booms to them as they orbit at such high speed in the atmosphere. Now, I've already mentioned how the light and dark regions of Jupiter and Saturn are due to the upward or downward motion, the convection currents of these ammonia clouds. So we also see that all of the planets, the giant planets, have bands, right? They have lines to them. Now, Uranus obviously has lines kind of the wrong way because it's tilted, right? The direction of rotation is what's determining these lines. So as the planets rotate, they're spinning. That's what's creating these strong winds. And for Jupiter, Saturn, and Neptune, these are sort of east to west rotation, east to west winds. Now, on Uranus, I should also mention that despite the fact that it rotates on its side, we actually don't see much change to its atmosphere, despite the fact that the poles, like we talked about, have 42-year day-night cycles. So Uranus is still able to redistribute the heat from the sun that it gets, and it's large enough that it has enough heat capacity that it doesn't seem to change in temperature much, even during these long, day or night spells. Okay, so then what about the storms? So this is where we'll have to end this chapter. But if you've ever looked at pictures, especially of Jupiter, we all probably have heard of the Great Red Spot in this picture here. A huge storm, incomprehensibly large hurricane, basically. And it's been going on for as long as we've been able to see it. So since Galileo looked at Jupiter, over 300 years, we have been able to see this giant storm. And what's strange about it is it seems to be losing energy. So it seems that as we've been watching it, and maybe in the next few decades, it could peter out. It could finally vanish. These storms, when they're large enough, just like hurricanes on Earth, they actually become sort of more stable in a way. Now, hurricanes on Earth, eventually they hit, Florida or somewhere, and they lose their energy as they go over a landmass. That doesn't happen on giant planets, and so this is why we see such persistent storms. They tend to live for many centuries, but they don't last forever. Now, interestingly, we saw a very similar, we call it the Great Dark Spot storm on Neptune, but it actually seems to have vanished by the time Voyager got out to look at it. And so this just goes to show these storms, we think of them as everlasting. Maybe they're long-lived for human scales, but they're not permanent. They come from complex physics where we get, plenty of the same types of physics on Earth, but just in these giant planets, they can persist for much longer. Okay, so that's where I'll leave it for now, but we'll continue on talking about the moons of these planets and the rest of the outer solar system in the next chapter.